Hello there, welcome to another problem session. So today we have a kind of interesting problem where you can think of that what happens if I shine light on say you have a metal plate like this is a silver plate, and you shine light directly on it. So the electric field is pointed that way, and magnetic field is pointed that way. So magnetic field is going back and forth in that direction, and electric field is going back and forth in this direction. So when it comes over here, electric field will going back and forth in that direction. That's the electric field, which is parallel. And so whatever the electric field is, inside the immediate path there is going to be just on the first layer. Electric field will be is parallel, right? Electric field is parallel. So electric field, if this is medium 1 and this is medium 2, so electric field, parallel part of electric field in medium 1 is equal to electric field in medium 2 parallel. So the wave part actually goes in. However, it gets damped. So if you look at this wave and I'm going to flip the coordinate like that and looking from here. So this is the z-axis, and so we have say this is the x, and that's the y. No, y is this way and z is that way. So if I flipped it, so I can actually draw it over here. I've already drawn it. So the electric field wave used to be this big coming in. So it's this yellow line is electric field waves. So it used to be that big, and it used to be like. So the coming in was kind of constant at that, but inside the metal it kind of decays, has same frequency as over here. So frequency F here, frequency F here, same frequency, but it kind of decays. And if you look at the top here, and the top is here, and the top is here, and you connect it, you get an envelope. So this is called envelope, and envelope goes as e to the power, if this direction is z, it's z over d, or delta. I'm going to call it delta, and delta is the distance at which from E0, this is actually 1 over e of E0. So it's gone down. Used to be amplitude E0 at z equal to 0, but it's actually 1e less than that. So over here, if you were over here, you will just fluctuate this and that. If you're over here, you're going to fluctuate just this is the 0. So you're going to fluctuate that much over here, and over here you're going to fluctuate that much over here. And so it's going to, if you're over here, you're going to fluctuate this much from the envelope back to the opposite of the envelope. This one will be over here. Actually, I drew another envelope down here and envelope here. So it's kind of like a horn, and you're going to be trapped in the horn, and the amplitude going down, 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 down. So this distance delta I'm writing is called skin depth. I will derive this once I solve this problem, but the formula is quite complicated. Depends on the frequency. This omega is 2 pi f. So it depends on frequency. Depends on epsilon mu of this metal. Okay. And sigma is the conductivity of the metal. So we're supposed to answer this question for a silver plate, for which mu is not a magnetic material, so mu is close to mu naught. Okay, and that's going to be the value like that. And epsilon is that this is quite complicated. Epsilon is very complicated property. So is mu, but epsilon is very complicated. And in metals, there are models of how to find out what the epsilon will be. So finding epsilon is same as finding this is constant. So this is called dielectric constant. And there are a couple of models of how you treat the metal, but that's going to be a little bit beyond our consideration here. We are actually, when you do this limit, we don't need to know the value of epsilon. Okay, we don't need a dielectric constant of. And if you want to do epsilon equal to 1, you can set that as a reference if you want, but we really don't need to know that. And silver, I think the silver's conductivity in SI units is 10 to the 7. Okay, hopefully I looked up correctly. A diameter of a silver atom I looked up, and this is that. So this will be helpful in finding B, but first we need to find skin depth in this approximation, which is like a low frequency approximation. So we are going to do the approximation and then plug in these numbers and see what we get. Okay, let me pause here. Okay, so how are we going to do this? If you look at a formula in any book, it's going to be this formula, but then I'm going to have to do this approximation. So let's see, when we do this, we can make a small number out of this. So omega over sigma over epsilon is a small number, is small, or sigma over epsilon over omega is large. So what does small mean? This is much less than 1. That's what this means, and this means much greater than 1. So if I do this, square it, this greater than 1 will be way greater than 1, and take a square root of it. So this will dominate over 1, and so our first step will be to get this thing out. And this thing just becomes sigma over epsilon omega. And because it's square root of everything, square root of epsilon, nicely, thing I don't need to know, which is complicated, cancels out in this approximation for low frequency. Okay, and this is considered high frequency in some consideration, like it's a radio frequency, but it's not as high a frequency as like a visible light. You know, this is 10 to the power 3 for that and 2 for that, 5 hertz. Visible light is 10 to the power 14 to 15 hertz. 14 to 15 hertz. So this is actually low frequency compared to visible light. Okay, so let's so this just turns out to be, skin depth turns out to be a square root of 2 in the numerator, and omega actually cancels out, makes this a square root of omega. So a square root of, I have omega, I have a mu, I have a sigma. Clearly we can compute this, okay, for these values. So I have a square root of 2, and then you have a square root of 2 pi f, 10 to the power 5 for 2 pi f, and mu is 4 pi times 10 to the minus 7, and then sigma is 10 to the 7. So this guy cancels out. So we can say this, make it a 6. So if make it a 6 and then divide by 10, so this 10 to the 1 is 3 will come out here. So this is 10 to the power minus 3. So that's like a millimeter, this millimeter. And so this square root 2, square root cancels out. So we have 1 over the square root of, you can say square root of 10 over 4 pi, all of this kind of, so this is 5 and 2 pi millimeters. Let me get this computed. So m dot square root 5 over 2 times m dot pi. So this is 0.89. So this is actually 0.9 millimeter. So it's pretty. It's not that much as 1 millimeter, right? So it looks like it does go inside. So here is a silver. So from here to here, this is 0.9 millimeter. So electric field is not 0 inside the metal. You might have heard a phrase that electric field is 0 inside a metal, and that only is true in electrostatics, when the electric field is statics. So if you have a metal, and you bring a plus charge here, then you will see electric field inside here is 0. Electric field outside is not 0. So for instance, when it goes up, it hits 90 degrees and goes up, hits 90 degrees, hits 90 degrees. And then what happens, positive charge actually distributes, pulls the negative charges, and these places maybe distribution of positive charges is such that from here, this electric field that should have continued from this guy, it still is continuing, but what's going on is there's a electric field inside from this positive charge to the negative charge of the metal polarization, and they cancel out inside the metal. So this is an electrostatic. In our case here, this electric field is not static. So here, when you have a non-static electric field, it can penetrate inside the metal. That's what I'm saying, and it can go quite far. Okay, so if you have this as one layer of atoms, if you imagine silver atoms are layer by layer, then by noticing that, you will say number of layers will be 0.9 times 10 to the 1 is 3. That half our distance have to go, divide by 2. Maybe just call it 3 times 10 to the minus 10. So this is 0.3 times 10 to the power 7 layers. So 3 million layers. Okay, so this solves this problem. But the question is, where does this come from? And that's an advanced treatment that I'm going to do now. It's going to be very long, and it's for maybe advanced students. So if you are an advanced student, stick around, and maybe I will set the whole problem up and find where this formula comes from. Okay. Okay, so where does this formula come from? Let me draw the coordinate. So we are in the silver, and this is x-axis, and this is the y-axis, and this is the origin. So in this medium, we have no free charge, no flowing current, applied current. If that would be the case if this was not a metal. So JF will be equal to sigma times whatever the electric field is. So whenever there is electric field, and because there's a freely flowing electrons, free electrons which can flow with even smallest amount of electric field. So if there's electric field here, it's going to flow. So that's why you're going to have a flowing current. And then you have a D equals to epsilon E, and then you have a B 1 over mu B equals to H, right? So, and the laws are del dot D equals to rho F, and rho F is 0, so it's going to be 0. Del dot B is always 0, and del cross E equals minus dB dt, and then you have a del cross H, which is equal to JF plus dd dt. Okay, so we want the solution of these guys, and these are the relations between them. And what kind of solution we want? We want a wave traveling in that direction. So we're going to use a complex notation for the wave, so because easy calculation complex notation. In general, you have for electric field, we want a plane wave. It says plane wave, so it will be some vector, and which will be complex e to the power I k dot r minus omega t. So it's going to be like phase is in here, and B will be, so this is E is at r at time t. This is at some location r time t, and it's going to be B0 e to the I. It's going to be, this phase will be the same. So we can actually plug into these guys, and right away we'll notice something. So this is complex, so we're going to write, this is, now we are doing complex, so this will become complex if we just do that, and in the end we want real part of this quantity to get the real part. So till we have this inside this thing, we have complex. So we can think of this whole thing also applies to complex. You can tilde over all of this to make it complex, okay? And we'll plug this in there and see where does it lead us. So when you do this, you have a k is the direction in which it's traveling. So you get k dot, this one del dot ik dot, this E0 vector tilde equal to 0. That means this E0 vector is perpendicular to k vector. That means E0 vector is perpendicular to k vector. This guy gives me pretty nicely ik b 0 tilde, so the 0 part. The other part will, when you work it out, I will encourage you to work it out and get what I'm getting. This will be B0 will be perpendicular to k vector. So this is what it's saying is if the k vector is in that direction, then E and B are perpendicular to it. Okay, so this is the xy plane. So E can be that way, B can be that way, kind of like this. How about this one? This one says ik vector cross too fast. Sometimes I get excited and write too fast. E0, this is complex part, equals to, becomes plus because when I take a derivative, this brings a minus I omega B0 vector tilde. Tilde is this is complex because everything here is complex, even the amplitude is complex. Okay, so it's a you can see that k, this I can cancels out. So if you just look at the real part, so real part of this will be k cross E0 equal to B0. It's like that. So this tells me that if this is k and this is E, then I do a right hand rule, the B will come out like that. So, and these are 90 degrees. So if this was, so if I take this guy along the x, along the y, along the z, then we'll have satisfied this. So from then on, I'm just going to do, rather than do a completely general calculation, we already know k is kz hat, and just take E naught as E naught x hat, and B naught is B naught y hat. Just let this, just for the simplification of calculation. Using that, let's do this guy. So using that, okay, let's do this guy, complete this. So this will be just k, there's omega missing here. K is complex also. We'll find out. Right now it looks like k is real, but we'll find out k has to be complex. But so far we kind of don't know it yet. So you have a k times E0 is equal to omega times B0, right? So it looks almost the same, but this will turn out to be a complex in the future. So let's keep together. Used to be E0 was C times B0, used to be in vacuum. Our E0 was speed of F times B0 in linear medium. And V was simply 1/* square root of mu epsilon. But it's not the case here. Okay, you will find out because this K is pretty complicated stuff. And that part of the complication is coming, skin depth in this formula, because the K is, this is actually, the denominator of this formula is actually equal to 1 over imaginary part of K. K will turn out to be K equals to K real part plus I times K imaginary part. And this part is what's related with the skin depth. We'll see in just a second. After I do all this algebra, then we're gonna get the fruits of our labor, okay? Okay, so this is the case. Now I do this. So this is gonna be I, K, cross H is gonna be B over mu. Mu is same everywhere, so del of mu is 0, so it's not going to impact that. And this one will be sigma times E, sigma E0 B0. And this will be epsilon E, so it's going to be epsilon minus I omega E. Okay, so and now notice that B0 vector times omega is equal to this, so we can get the entire equation in terms of E0. So we write down I k cross mu times omega, and this is k cross E0 tilde. So I get this, and if you want to I, multiply by minus I everywhere. So if you makes it 1, and this becomes minus I, and this becomes 1. So that we don't have to write I on this side. And so that's equal to minus I sigma E0 tilde plus epsilon omega E0 tilde. Okay, now I can use this special case to simplify this, and everything is perpendicular, so all going in the same direction. And let me get some more space. Okay. Oh, I just noticed while I was copying that I had multiplied this whole thing by minus I to make this a plus 1, and this is minus I. Minus I is actually minus here. Minus I with minus I, that should be equal to plus I square, would be minus 1. So there was a sign error. Yes, when you do something like this, you have to be very careful. Okay, so this is k square E0 tilde and over mu omega, and this is in the z direction, so z hat cross z hat cross x hat. So this becomes y hat, and this becomes minus x hat. So the left side is going to be minus k square over mu omega, and E0 will cancel from every one of them. It's going to be minus I sigma minus epsilon omega, so plus, so k square is equal to plus I mu sigma omega plus epsilon mu omega square. Okay, so omega is real. Omega is 2 pi f, which means from this we're taking this real, although this can be complex, but we're just going to take that as real. Then k is real. So this is the real part of k square, and this is the imaginary part of k square. So k can be k real plus ik imaginary, right? But this k square, so the k square is kr square minus ki square plus I times 2 kr ki. So this stuff is that, and this stuff is that. So you can see it can become very nasty calculation, but how to get kr and ki. Okay, so you probably if you have done some complex algebra, you probably will be able to get that. But let me write the answer for you, and I'm not going to work out this calculation, and maybe I'm going to use that calculation just to show you that where does this skin depth this thing follow. Okay, how does this skin depth follow from this? So this is going to be our main claim, and so when we compare this and try to solve for kr and ki, we get pretty complicated expressions. Okay, and let me just copy it from my notes. So a kr and ki are these complicated expressions which you can solve by just from this and substituting and square rooting and square rooting again, and then you're going to get this answer. Okay, I'm going to pause and transfer it over there and show what's the meaning of these things in our particular situation. So first, note that this is in the when z is greater than 0 is in metal. This is not the case when it's over here. Okay, it's only in this area, in this volume. All right, so in this volume, at any point we have electric field at x, y, z, t. Is actually only depends on z and t, because we're looking at just as something is traveling in a plane wave, zt, and it's some kind of amplitude which we haven't really found yet. It's just say this one is actually E0, and in x hat e to the power I phi e. So this is complex part of that. So we're supposed to take a real part of this for our solution, right? So we have that, and then I've got the e to the power I k z, then times e to the power I omega t minus I omega t. And we usually write this together, right? So let me write this together as I've done before. So minus omega t. But now notice that this thing is actually becoming k real plus I k imaginary. And put it in there, you will see that this factor, which depends on space and time, this start to become really interesting. E to the power minus k imaginary z, and this becomes totally real. E to the power I k real z minus omega t. So this is real. If you pull all of this out, I have an x side which is real. You have E0 is real. E to the power minus ki z, which is real, and the real part of e to the power I k r z minus omega t, and e to the power I phi e, which we haven't found phi e, but it's the phi e. We're just looking at the explanation of skin depth. So this will just be a cosine. So this will be x at E0 e to the minus k I z cosine k real z minus omega t plus phi e. So this is actually the electric field. We can do similar thing for the magnetic field. Now you see, it used to be, notice on this side, this is the amplitude with which this fluctuates. This fluctuates, right, between -1 and 1. So this multiplies, that's going to wave fluctuate. But as it's going along the z-axis, this is going to actually drop. If you just look at that, that's the envelope. So it's gonna just go like that. If it's negative, E0 is gonna just, but it drops. Yeah, so if it's 1 here, becomes 1/3 or 1 over E at this time, and let's call it distance to delta is d. So if you go E0 equals ki delta, it becomes 1 over E of E0. So of course E0 goes away, and so ki delta equals to 1. So delta equals to 1 over ki. And this is the one written down over there, 1 over ke, k imaginary part of the wave vector is what is called skin depth. So this is a long explanation. There is a interesting thing, I kind of erased that, but let me bring that back, and I'll tell you that the phase of the magnetic field is also not the same. So maybe you can do it out, okay? This is advanced, so you should do it out. Maybe do it, and I shouldn't do it because the video is getting very long. That if this is the case, and B is y naught B0, it's a minus kiz cosine kzr minus omega t plus phi b, you're going to find out that phi b and phi e are not equal to each other. Phi b is not equal to phi e in metal, and find the difference. This is only for advanced students, and you can do this by using complex algebra. Just because suppose somebody want to do the algebra, let me tell you the answer so you can check your answer. Okay, you may want to carry out this calculation to show these things. If you're comfortable with complex algebra, using complex algebra, you can actually do it pretty readily. So I will leave it there, and if you like this kind of explanation, you can hit the like button, and I'll see you in the next video. Bye.